Hi everyone. In this video I want to go over 3 online homework problems that have to deal with reaction mechanisms. And you will be expected to know how to determine the rate law expression for an overall reaction depending on where the slow step is, either step 1 in the first case or step 2 in problem 2. Okay, alright. The 3 problems are here. I already have done them and I'll go over my answers in the video. But if you want, go ahead and take a screenshot or copy each problem and try it on your own. Use your notes, use the equations that you've been given in class. So here's problem 1. Problem 2 is similar, except now instead of the slow step being step 1, you notice that in problem 2, the slow step is in step 2. And then in problem 3, you're given the overall reaction and the first step, but you have to come up with the second elementary reaction. Each of these steps are called elementary reactions. Okay? Let me get the first one up. Again, I would take this opportunity to try these problems on your own before taking a look at my answers. Okay. In problem number 1, you are given 2 elementary reactions, step 1 and step 2, and I've assigned step 1 to have a rate constant of K1 and step 2 to have a rate constant of K2. K1 is much less than K2, meaning that K1 is the slow step. This is the easier of the 2 problems where you have to figure out the rate law. You want to see the first step be slow because if the first step is the slow step, then the rate law for step 1 is the rate law for the overall chemical reaction. But before we get to that rate law, part A says write the overall chemical reaction. You just have to add the 2 reactions and cancel out anything that occurs on both sides. You notice that F, single atom F in the gas phase, there's 1 mole each on the reactants and the product side, so they cancel out. Let's see what I wrote. So I wrote 2NO2 plus F2 gives us 2NO2F. We want to make sure that the equation is balanced and that the coefficients are in the lowest whole number terms. Okay? There should not be any fractions here. Okay, write the rate law for the overall chemical reaction. Oh yeah, good. So I restated the 2 elementary reactions and I labeled which one's a slow and which one's a fast. And this is the good case. This is the easier case because if the first step is slow, its rate law for the elementary reaction is the rate law for the overall chemical reaction. And don't forget, in the elementary reactions, in the step reactions, you're supposed to use the coefficient as the exponent. But in this case, all of it is 1. So let's take a look at the rate law for the first step. It's just NO raised to the 1 times F2 raised to the 1 times the rate constant. Is that it? Yep, that's it. Okay, so that is the answer for write the rate law for the overall chemical reaction. It is actually identical to the rate law for the first step elementary reaction. Easy. Part C, write the rate constant K for the overall chemical reaction in terms of K1 and K2, and if necessary, the rate constants for the reverse directions. So K minus 1 is going from the right to the left for step 1. K minus 2 from the right to the left for step 2. What is this about? Well, a constant is a constant, okay, but um, the rate constants for each of these processes are different, whether you're going in the forward direction or reverse direction, whether it's step 1 or step 2. They want us to know what is the K for the overall chemical reaction in terms of these Ks. This is easy. I think I made it sound harder than it really is, since the overall rate law for the chemical reaction is this, and it's equal to the rate law for step 1. Well, the rate law for step 1 is K1, right? K1 times the concentrations of NO2 and F2. If you want, you could even label it. You put the K above K1, and this is K2. In the reverse direction, the convention is to put a negative sign, K minus 1. Okay. Yep. So, actually, the K of the overall rate law for the chemical reaction is equal to the K1, the rate constant for the step 1. That was easy, or that was meant to be a warm-up for problem number 2. Problem number 2 is difficult, or not difficult, but more steps to solve, because in problem number 2, the slow step is actually step 2, not step 1. And there's a problem when that happens that I'll show you how to fix. So now, step 2 is slower. It's called the rate determining step. Remember that, RDS? Part A is standard. Write the overall chemical reaction. Again, we have the intermediate. In this case, it's a single atom of O. So those go away. And then, okay, it looks like 2NO plus O2 gives 2NO2. And it's balanced. Write the rate law for the overall chemical reaction. Okay, so I didn't label what's fast and what's slow. This one's slow, and this one's fast. So the rate law for the slow step, for the elementary step, is this. Rate equals K2 concentration of O times the concentration of NO, both raised to the power of 1. And that would be the rate law for the overall chemical reaction, except for the fact that that single O is not either the reactants nor the product. You have to express the rate law for the overall chemical reaction in terms of the compounds that are actually in the reaction. So we got to replace this. And I think I wrote that down here. This is just a reiteration. This is harder than problem 1 because the slow step is the second step, and its rate law has a molecule not in the overall chemical reaction. Right? It has a single atom O in its rate law expression. Okay, good. So I wrote down the rate law for the second step, okay, realizing that I have to replace this concentration of O. I'm going to use this step 1 and the fact that the forward rate is equal to the reverse rate. So now I'm going to use the rate law for this to figure out how to replace this O. Okay, so how do I do that? I set the forward rate and the reverse rate identical to each other. Do you remember how I talked about the K1 for the K for the first step is K1? If you want, let's take a look at that. So that is right here. NO, concentration of NO times the concentration of O2. In the backwards direction, it's K minus 1 times the concentration of O times the concentration of NO2. Those rates have to be identical. They're both positive. A rate is a positive number, like speed, miles per hour. You can't go negative 25 miles per hour. So both of these are positive, and they're set equal to each other. There's the O that we got to solve for so we could replace this O right here. What did I do? I took those two terms and I divided both sides by these two terms. So now I isolated O. You are taking this expression and you are substituting it right there, and you're getting rid of this. When that happens, you notice that we have NO twice. So I would expect the concentration of NO to be squared. I'm also carrying the K's, the specific K's, the K1 and the K minus 1 up to here. And, okay, good. I get this as a rate. Now, this is the rate law for the overall chemical reaction, because I had replaced this O with all of this junk right here. Now the thing is, a constant times a constant divided by a constant is a different constant, but it's still a constant. And you'll still use that constant number and plug in your concentrations to figure out the rate. Okay. So we're going to summarize or sum up all of those constants as a new constant, the constant for the overall reaction, the rate constant. Now, there's something odd about this, and I admit it's odd. This may be the first time you've seen a rate law expression with something in the denominator. Okay, but that's perfectly fine. Okay, it happens, especially when you're doing, these substitutions. The other thing, and maybe this is the one that's even more surprising, is that NO2 is a product. So this may be the first time that you saw anything in the denominator, but it's probably one of the first times you've seen a product concentration in the rate law. Right? Normally it's, if you have A plus B equals C, it's the rate equals K times the concentration of A times the concentration of B, period, raised to their exponents, M and N. But here, yeah, we have a denominator, and it is a product. Perfectly fine. Perfectly fine. That happens because, the product concentration has an effect now of the rate. And it looks like the more product we get, right, the more product we get, the lower the rate. So it's almost like it knows it's done. Like you're getting too much product, you're going to slow down the rate. The last problem, C. We did this before in problem 1. Write the rate constant K in terms of these other rate constants. Well, we had done that already. You see how I combine K2, K1, K minus 1 into a new rate constant for the overall chemical reaction. So that's what they're expecting. All right, go through this again. I know I went through this a little bit fast, and I didn't literally write this out in front of you. I just explained my answer. Okay, at first it may be a little bit tricky, like what happened here? Why do we get this conglomeration of K's? But that's only because we had this originally for this step 2, the K2, and then when we substituted this concentration of oxygen, we brought in the K1 and the K minus 1. No big deal. Just have to go through this stepwise and try it one more time on your own without the answers. Okay. Problem 3. Easy concept, but maybe you're not getting a lot of practice with these types of problems. You're more concerned, I know, with the rate law and trying to figure out the rate law depending on where the slow step is. This one's a little bit different. It's actually easier, but it's less common to see. You have an overall reaction. Okay, so they gave you that. And they told you in this problem that you have a two-step mechanism, two elementary reactions, and they only gave you the first step, and you have to figure out the second one. This is just like Hess's law. Like, you have to pretend, what do I need here, so when I add these two up, I get the result? So the first thing I notice is that you produce an O in the first step, but there is no single oxygen in the overall reaction. We got to cancel that oxygen. I think that's where I would go first. You need O gas as a reactant in step 2 to cancel it in step 1. What else do we need? Oops, I cheated. We have one NO on the product side, but we actually need 2 for the overall reaction. So I need the products to give me NO. So I need NO. Oh, I also need O2 because O2, we don't see it yet in the elementary reactions. So I need NO, 1 NO, to equal 2 when we add them up, and we need 1 O2 as a product of step 2. I think we're good with the products. Those are your products. That's one of your reactants. But they gave us a hint that this elementary reaction, I say step here, but same thing as elementary reaction, it's bimolecular. There has to be two things reacting. And I already have the O. See? I have 2 NO2 in the overall reaction. I've only taken care of one of them. So if you put everything together, so I'm trying to figure out what that is, but I now realize that I need 2 NO2s, not just one. And that's your final answer. For step 2, you should write oxygen plus NO2 gives you NO plus O2 gas. And it is, double check before you go on to the next problem, it is balanced. Okay, those are 3 problems dealing with reaction mechanisms. The first one, the slow step is step 1. In the second problem, the slow step is step 2. And in this problem, you have to fill in the blank, fill in the missing elementary reaction.